Welcome to the Sleepless Scientist, a quiet corner of the cosmos where the whispers of science settle into your thoughts like stardust on a still night. This is a place where knowledge drifts softly into the folds of your consciousness, where the universe doesn't shout but gently hums, guiding you toward understanding and, perhaps, sleep. Tonight, beneath the hush of stars and logic, let us unfold a question that glimmers in the dark like a solitary photon rushing across the void. What makes light the fastest thing in the universe? Thank you for choosing to spend your time here. If this video keeps you awake, I sincerely apologize. But if curiosity is the cost of restlessness, it is a fair trade. Please consider liking, sharing, and commenting where in the world and what hour of the night you're listening to this gentle inquiry. Light, a word so short and simple, yet so profoundly complex. It is something we see, something we feel, something we often take for granted. But behind that everyday experience lies a phenomenon of almost unimaginable speed and consistency. Light travels at approximately 299,792 kilometers per second through the vacuum of space. That's nearly 300,000 kilometers every second. Fast enough to orbit Earth more than 7 times in the blink of an eye. Nothing else we know of moves faster than light in empty space. Not sound, not bullets, not spacecraft, not even the gravitational pull of collapsing stars. Light is the ceiling, the upper limit, the fastest entity the universe allows. But why? Is it so fast? Why not sound or matter or energy in other forms? What is it about light that earns it this unmatched velocity, and what keeps everything else lagging behind? To begin to answer, we must first understand what light truly is, not just what it looks like, but what it does, how it behaves, how it moves. Light, fundamentally, is a form of energy. It is part of the electromagnetic spectrum, a continuum of waves that also includes radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. All of these are forms of electromagnetic radiation, differing only in their wavelength and frequency. What unites them is how they move. All travel at the same speed in a vacuum, and all obey the same physical laws. When we speak of light as the fastest thing in the universe, we mean electromagnetic radiation in its entirety. A gamma ray from a collapsing star, a radio wave from a distant galaxy, and the visible light from your lamp all move at the same extraordinary pace. The defining feature of this speed is not set by how powerful the source is or how intense the beam might be. It is instead embedded in the very fabric of space and time. This speed, often denoted simply as the speed of light, is not just about how fast photons move. It is a fundamental constant of nature, woven into the equations that describe the behavior of the universe itself. Consider this. The speed of light is not just a number that came out of an experiment. It is a cosmic speed limit, an unbreakable wall that nothing can breach. Why that number and not another? Why not slower or faster? The answer lies not in preference, but in the structure of the universe. Space and time are interlinked in ways that defy ordinary intuition. Their relationship is calibrated so that this speed, this precise, finite value, is not just the speed of light, but the maximum speed at which information or energy can travel. Change the speed, and the entire structure of reality unravels. The constancy of this value gives order to time, structure to space, and meaning to causality. In essence, light speed is a consequence of the universe's geometry. Space and time are not static backgrounds. They are dynamic, responsive, and shaped by the very things they contain. When something moves, anything it interacts with. This fabric, the less massive it is, the more freely it moves. A photon, which is the quantum particle of light, has no rest mass. This absence of mass liberates it from many of the constraints that affect other forms of matter or energy. Without rest mass, it is not tied down. It can never be at rest. From the moment it is created, it moves at one speed only, the maximum allowed speed. It doesn't accelerate to this speed. It exists already at this velocity. Always. Imagine this: if you could become a photon and see the universe from its perspective. A thought experiment, not a literal possibility. Time would appear frozen. Distance would collapse. From the photon's point of view, which is a philosophical concept more than a physical one, it travels from point A to point B instantaneously. But from our perspective, rooted in time and space, the journey unfolds across seconds, minutes, years, or millennia. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. Light from the nearest star, Proxima Centauri, takes over 4 years. From galaxies at the edge of our visible universe, the light we see now began its voyage more than 13 billion years ago. In these numbers, we find not just speed, but patience, a patience only light can afford. The vacuum of space, devoid of matter, offers the perfect stage for light's unimpeded travel. Unlike sound, which needs molecules to vibrate through, or particles that bump and grind against each other, light requires no such medium. It moves not by pushing, but by oscillating. Electric and magnetic fields dancing in harmony, perpendicular to each other and to the direction of motion. This oscillation is not disturbed by the emptiness of space. Instead, the void is what allows light to move freely, unstopped, unfiltered, unburdened. Yet light's interaction with the world is far from simple. When it enters a material like glass or water or even air, its journey shifts. It slows, not because the light itself is changing speed, but because it is being absorbed and re-emitted, its path detoured by the atoms it encounters. In diamond, for instance, light can slow to just 124,000 kilometers per second. Still fast, but not the cosmic maximum. The more optical density a material has, the more it hinders light's progress. But once light exits the material and re-enters the vacuum, it resumes its full speed as though nothing happened. This is the nature of a fundamental constant. It cannot be broken, only delayed. This behavior reveals something deeper. Light is not just a wave, not just a particle, not just energy in motion. It is a probe, a messenger, a time capsule. Everything we know about the distant universe comes to us through light. Every galaxy we've mapped, every star we've analyzed, every planet we've seen beyond our solar system, they were revealed by light's tireless travel across vast gulfs of space. Some of this light left its origin long before our planet even existed. Yet here it is, completing a voyage measured not in days or years, but in epochs. Why is light the fastest? Because it has to be. Not for our benefit, not for convenience, but because the universe made it that way. 'Tis not an advantage, it is a necessity. The constancy of this speed gives rise to the very notion of simultaneity, causality, and observable motion. If light were slower or faster, if it varied, if it were inconsistent, our entire understanding of space, time, and energy would collapse. Light speed is not just a number in a book, it is a law written into the bones of reality. We think of speed as power, as strength. But light speed is not a brute force. It is precision. It is elegance. It is the disciplined sprint of something that must always move, that has no home in rest. It is the reason we can look up at the night sky and see the history of the cosmos unfolding in faint glimmers. It is the thread that ties us to the birth of stars, to the echo of the Big Bang, to the stories written in ancient beams that took billions of years to arrive. Light is more than just a vehicle of speed. It is a storyteller etched into the very architecture of spacetime. As photons race across the universe, they do not carry only energy. They carry information, patterns, and the chronology of events too distant or too ancient for any other messenger to preserve. In their journey, they bypass all barriers of language, scale, and matter, crossing expanses where nothing else could survive the emptiness. It is through light that we read the universe like a history book stretched across the abyss. Every flicker from a star, every pulse from a quasar, every soft afterglow from the birth of time itself is captured in the arrival of light, moving at its inexorable pace. And this journey, always at that same ultimate velocity, is the most faithful chronicle the cosmos provides. There is a profound clarity in the way light adheres to this universal boundary. Its unwavering speed anchors the structure of physics, giving definition to time and order to motion. When scientists calculate the age of the universe, they do so by measuring the redshift of light. When they determine the composition of stars, they read the spectral lines embedded in starlight. When they map the most distant reaches of the observable universe, they are not exploring through presence. They are decoding echoes, images, and energies ferried by light. In all of these pursuits, light speed is not just a tool. It is the metric by which everything else is measured. The centrality of light speed extends beyond cosmology and into the structure of matter itself. Electrons respond to changes in electric fields at speeds governed by the same fundamental constant. Particle interactions within atoms occur in accordance with it. Even the ticking of atomic clocks, those paragons of temporal precision, rely on electromagnetic transitions dictated by light's immutable properties. The very synchronization of global navigation systems depends on the assumption that light speed is fixed and universally consistent. If it were not, our concepts of distance, timing, and simultaneity would be meaningless. GPS satellites, for instance, must account for relativistic effects where the constancy of light speed remains a pivotal anchor, balancing the warping of time and space experienced in orbit. From a philosophical perspective, the idea that light is the fastest thing in the universe challenges our instincts. In a world governed by action and reaction, by forces and friction, by visible causes and tangible effects, it seems odd that something so insubstantial, so intangible, could be the paragon of velocity. Yet light is the harbinger of causality. It defines what can be seen and what remains hidden, what can influence what, and when. If you shine a flashlight into the darkness, the beam doesn't instantly illuminate a distant wall. The photons still obey their limit, reaching that wall only after traveling the intervening space at their fixed speed. That lag, imperceptible to us over short distances, becomes monumental over astronomical scales. This lag isn't just a delay, it's a boundary of knowledge. There are regions of the universe we cannot observe, not because they are hidden behind clouds or obstacles, but because their light hasn't had enough time to reach us. We live in what's known as the observable universe, a spherical region centered on Earth and bounded not by geography, but by time and light. Beyond this boundary, the cosmos may continue indefinitely. But until their light arrives, those parts are silent to us. In this sense, the speed of light doesn't just govern motion, it governs awareness. It sets a horizon on what can be known, on what has had the opportunity to present itself. Yet this limit also grants profound opportunity. Because light speed is finite, we are always seeing the past. We do not see stars as they are, but as they were. When we look at the moon, we see it as it was 1.3 seconds ago. The sun, as it was over 8 minutes ago. The Andromeda galaxy, as it was 2.5 million years ago. And the most distant light ever detected. Cosmic microwave background radiation shows us the universe as it was roughly 380,000 years after its birth, nearly 13.8 billion years in the past. This time, delay turns the sky into a museum of time, a panorama where every pinprick of light is a window into a different era of cosmic history. Such is the paradox of light speed. It is the fastest possible motion, yet also a conveyor of delay. It is what allows us to know, yet also what defines the edge of what can be known. In its fidelity to its limit, it reveals not just the structure of physics, but the texture of time. We often imagine that faster is better, that a higher speed implies a more advanced technology, a more powerful force, a greater capability. But light reminds us that some limits are not constraints, but the very scaffolding upon which understanding is built. It is not that light breaks records, it sets the record. It is not that it races ahead, it defines the racetrack. Every equation that models the cosmos, every simulation that predicts stellar birth or planetary orbit, every thought experiment about time travel or wormholes or cosmic expansion, all of them hinge on the constancy and supremacy of light's velocity. Even in the realms of theoretical physics, where ideas like warp drives and hyperspace swirl with possibility, light remains the benchmark. It is the canvas on which every other concept is drawn. There is, of course, the enduring allure of imagining faster-than-light travel, wormholes, quantum entanglement, and hypothetical particles like tachyons all exist as speculative windows into what lies beyond the limit. But to date, no physical evidence supports any phenomenon that transmits matter, energy, or information faster than light. Quantum entanglement, while fascinating, does not transmit usable data faster than light. It only reveals correlations when both halves of the system are compared. It preserves causality, the order of cause and effect, which would otherwise unravel if information could leap past light's barrier. This boundary is more than theoretical. It is deeply observed, meticulously confirmed, and universally consistent across all experiments in all conditions. In every direction and in every frame of reference, the speed of light in vacuum remains the same. Whether measured from Earth or in deep space, in motion or at rest, by scientists using different instruments and methods, the number remains unshaken. It is not merely a high speed, it is a principle. It is invariant, the same for all observers, regardless of their motion. This invariance is not just a detail, it is the cornerstone of modern physics. This is why the speed of light holds such reverence in the scientific world. Not because it dazzles with its velocity alone, but because it binds the laws of nature together with unflinching consistency. It anchors the theory of relativity. It governs electromagnetism. It informs quantum field theory. It is the very ruler by which space and time are stitched into a coherent whole. Without it, no clock would tick in rhythm, no planet would orbit predictably, no signal would arrive with certainty. And yet, in its great speed, there is also humility. Light does not boast or blaze only in the spotlight. It is just as present in the glint of a dewdrop as in the glare of a supernova. It flickers in the lowest candle flame, reflects softly off ice, filters through leaves, paints rainbows in mist. The fastest thing in the universe is also the gentlest. It can warm or burn, blind or reveal, dazzle or soothe. But in every case, it arrives with the same silent, dignified consistency. And so we return to the question, what makes light the fastest thing in the universe? It is not merely its nature. It is the universe's need for something to anchor. The flow of cause and effect. Light is not fast because it tries to be. It is fast because that is the only speed at which a massless particle can exist. Anything slower would not be light. Anything faster would not be possible. In its speed, we see the fingerprint of the universe's order, a speed that is not broken, not surpassed, not improved, but honored. To contemplate light's unrivaled speed is to stare into the core of how the universe operates, not only in movement, but in communication, structure, and evolution. Every process that unfolds in time, every rhythm of atomic clocks, every moment of synchronization across space relies upon this fixed and unfaltering speed. Without it, the ticking heart of the universe would lose its beat. What we call the speed of light is not merely how quickly photons travel. It is the rate at which information propagates through space-time. It is the tempo of reality itself. If a signal could move faster, it could arrive before it was sent, disrupting the logical flow of cause and effect, introducing paradoxes that tear the fabric of understanding apart. The speed of light is not just fast, it is necessary for coherence. This necessity becomes more apparent when we consider relativity. As one moves closer to the speed of light, time begins to behave differently. An observer traveling at such speeds experiences time dilation, where seconds stretch, and the familiar rhythms of clocks begin to falter. Distance, too, contracts along the axis of travel. These effects are not illusions. They are measurable, observable, and real. At 90% of the speed of light, time slows down significantly for the traveler compared to someone at rest. At 99%, even more so. But no matter how fast one goes, light remains just beyond reach, forever unattainable to anything with mass. To accelerate a massive object to light speed would require infinite energy. It is not just impractical, it is fundamentally impossible. The closer one approaches this threshold, the more resistance the universe presents. The rules tighten. The mathematics become unforgiving. Nature protects the speed of light, not as a courtesy, but as a boundary between what is physical and what is hypothetical. This preservation of the light barrier is what maintains the consistency of events, the integrity of observation, and the trustworthiness of physics across the cosmos. Even in the domain of black holes, those enigmatic invisible engines of gravity, the importance of light speed becomes evident. A black hole is defined by its event horizon, the boundary beyond which not even light can escape. This is not because the black hole slows light down, but because space itself becomes so warped that all paths curve back inward. It is the ultimate demonstration of light's role as the outermost runner in a cosmic race. If even light cannot flee, then nothing else can. The event horizon is the edge of communication, the place where knowledge ends, where the familiar laws of physics dissolve into singularities and silence. Elsewhere, light continues its journey unfazed. In interstellar space, it travels for thousands or millions of years without interference. In the early universe, however, this was not always the case. For hundreds of thousands of years after the Big Bang, the universe was so hot and dense that photons could not travel freely. They were constantly scattered by particles in a dense fog of plasma. Only after the universe cooled sufficiently, around 380,000 years post-Big Bang, did light decouple from matter and begin its long voyage across the cosmos. That ancient light is still with us, stretched by the expansion of space into the microwave part of the spectrum. It is known as the cosmic microwave background, and it is the oldest light we can see. The afterglow of creation frozen in place by the finite speed at which it traveled. The precision with which we measure this light's properties tells us how space has stretched over time. Light waves elongate as the universe expands, a process known as redshift. The more distant a galaxy, the more its light is redshifted. It takes longer to arrive, and its wavelength grows. This subtle stretching carries with it information about the universe's rate of expansion, its curvature, its contents, and even its ultimate fate. Without light's constancy and speed, this cosmic archaeology would be impossible. We would have no access to the deep past, no way to chart the transformation of the universe over billions of years. Even closer to home, light reveals more than just the visible. Through telescopes sensitive to various parts of the electromagnetic spectrum, scientists peer into places otherwise hidden. Infrared reveals the heat of new stars cloaked in dust. Ultraviolet exposes the energy of stellar nurseries. X-rays uncover violent collisions and explosions. Radio waves trace the structure of gas clouds and the whispers of pulsars. Each of these types of light carries its message across space, all obeying the same speed limit, all following the same rhythm regardless of wavelength or energy. This consistency unites every corner of the universe, every field of astrophysics. Under a single, universal principle, light moves at the same speed, everywhere and always. This also means that light defines what is possible in the transmission of knowledge. When we communicate with distant spacecraft, like those orbiting Mars or sailing past the edge of the solar system, there is a delay. Signals sent from Earth take time to reach them, and their replies take time to return. At Mars's closest approach, the delay might be as little as 3 minutes. At its farthest, it stretches to 22 minutes or more. For Voyager 1, now beyond 24 billion kilometers from Earth, a message takes over 22 hours to reach us. This lag isn't a technological failure. It is a consequence of the fact that information cannot move faster than light. No matter how advanced our instruments, no matter how perfect our coding, we are constrained by this immutable law. This constraint, paradoxically, also preserves fairness in the universe. Without a maximum speed, cause and effect could be reversed. Simultaneity would become subjective. Confusion would reign across distances, but light speed fixed for all. Observers anchors every experience in a shared framework. Two observers moving at different velocities may disagree on when things happen, but they will always agree that light moved between them at the same speed. This uniformity is not trivial. It holds together the logic of relativity, the coherence of observation, and the trustworthiness of all scientific inference. In the laboratory, light also plays an intimate role. Laser pulses are used to measure time intervals down to femtoseconds, quadrillionths of a second. Optical tweezers use focused light beams to hold and manipulate particles, even biological cells, without touching them. In quantum computing, photons are envisioned as qubits, units of information that may one day surpass classical bits. In each case, light is both the tool and the medium, the instrument and the bridge. Its speed is not just theoretical, it is deeply practical, deeply reliable. And yet, for all its reliability, light is elusive. It cannot be held, has no rest. Mass, it leaves no trace unless it interacts. And when it does interact, when it reflects, refracts, refracts, or absorbs, it does so with subtlety and nuance. It paints the world with color, reveals texture, enables vision. But it also tells deeper truths about motion, temperature, chemical composition, and spatial arrangement. Light speed makes it a messenger, but its behavior makes it a decoder of reality. From the spin of electrons to the collapse of galaxies, light does not merely race ahead, it reveals. One might imagine an alternative universe governed by different constants, where the speed of light is not so central. But in such a universe, matter might not form. Atoms might not hold together. Energy might not transfer predictably. Causality might dissolve into chaos. The very shape of reality depends on the rules light plays by, and on the ceiling it enforces. This ceiling is not a cage. It is a framework. It ensures that events unfold in a way we can comprehend, analyze, and learn from. Light speed is the drumbeat to which everything else must march. In the end, the mystery of why light is the fastest thing in the universe may not be solvable in the way we solve other scientific puzzles. It is not a phenomenon with a simpler cause. It is a definition, a foundation, a given. The moment a photon is born, it moves at that speed, not less, not more. And that movement becomes a reference point for everything else. Motion, energy, perception, and the possibility of knowing anything at all. Light's relentless journey across the cosmos is more than an act of motion. It is a passage of continuity, a thread woven through all space and time, binding past to present and distant to near. It is often said that light does not age, and though this is a poetic notion, there is a scientific core beneath it. Because photons travel at the speed of light, they experience no time from their own perspective. Time does not tick forward for them as it does for us. From emission to absorption, from the moment they burst forth from a nuclear reaction in the core of a star to the instant they enter an astronomer's telescope lens, they remain ageless. This timelessness is not metaphor. It is a consequence of the very rules that govern the universe. To us, the journey of light across space can span millions or billions of years. But for the photon, if it could be said to possess a frame of reference, the emission and absorption are the same event. The implication of this is deeply profound. The light from a supernova that exploded in a distant galaxy before Earth ever formed is only now reaching us, illuminating our night sky, telling us of events long concluded, of matter long transformed. Yet that light, traveling all this time, has not changed in age, only in wavelength. Stretched by the expanding universe, elongated by time's fabric as it carries its unchanged message to us. And so we realize that light is a mechanism of preservation. In its finite speed and ageless movement, it stores the histories of distant worlds and bygone epochs. It records the unfolding of the cosmos in a way that no archive could rival. While sound fades, while memory distorts, light preserves the truth of what was. Even when the source no longer exists, the light remains, lingering like a footprint in the snow, untouched by the passage of its own origin. This property becomes more powerful still when we consider gravitational lensing, the bending of light by massive objects. Massive bodies like galaxies and black holes warp space itself, curving the paths that light takes around them. This isn't a bending in the traditional sense, but a consequence of geometry. Light always follows the straightest path through space, but space itself is curved. So as light journeys past massive structures, its path appears deflected. This effect allows astronomers to see behind cosmic objects, to view duplicate images of the same quasar, or to detect otherwise invisible matter. Once again, light's speed is central, not only to its motion, but to how it behaves when space is not flat, when the terrain is warped by gravity. Through these bends and delays, we learn not only about the light's origin, but also about the terrain it crossed. We can measure the distribution of dark matter by how it distorts light's path. We can estimate the mass of distant galaxies, not by their brightness, but by how they stretch and shear the background light flowing past them. This cosmic lensing reveals the scaffolding of the universe, not in particles or dust, but in warps and bends, made visible only through light's passage. Indeed, much of our knowledge about the universe's expansion comes from observing how the light of distant galaxies shifts in color. As the universe expands, the space between galaxies stretches. Light traveling through this expanding space is stretched too, its wavelength shifted toward the red end of the spectrum. The farther away a galaxy is, the more red-shifted its light becomes. Its pattern reveals the history of the cosmos, allowing us to chart not only its size and shape, but its acceleration. It is through the redshift of ancient light that we discovered the presence of dark energy, a mysterious force driving the expansion of the universe faster and faster. Without light's consistent speed, these measurements would be meaningless. The stretching of wavelengths would become muddled. The timing of photon arrivals would be uncertain. The very data on which we rely would disintegrate. But with the certainty of light's speed, we can decode the signatures of cosmic evolution. With confidence, the echoes of the early universe reach us not just as random noise, but as a coherent signal, encoded in light, transmitted faithfully for billions of years. This consistency has also enabled one of the most precise accomplishments in all of Science, the measurement of the fundamental constants of nature. Using lasers and atomic transitions, we've been able to define the meter not by an artifact of metal or stone, but by the distance light travels in a specific fraction of a second. The second itself is defined in terms of the vibrations of cesium atoms, and those vibrations are interpreted through light. This entwining of time, space, and light into a single, unified system of measurement is not arbitrary. It is elegant and necessary. It reflects a deeper truth about the universe, that at its most fundamental level, the laws of physics are written in the language of light. Even as we build technologies that push the limits of precision, quantum sensors, high-frequency clocks, photonic computers, we remain tethered to light's behavior. Fiber optic cables, which form the nervous system of our global communications infrastructure, carry data at speeds approaching that of light in glass. GPS satellites use timing signals based on light speed and must account for both special and general relativity to provide accurate positioning. Our growing dependence on these technologies is a quiet testimony to how deeply we trust the reliability of light's motion. But it is also a reminder of how much we are shaped by what we cannot surpass. Light speed is not just a limit, it is a law, one that humbles and defines us. As curious creatures, we often fantasize about what lies beyond, about faster travel, about skipping across the stars with ease. But every dream of the future must wrestle with the immovability of this speed. In every science fiction story, in every speculative leap, the question remains, what happens if we try to go faster than light? The answer, according to our current understanding, is simple. We cannot. Not because we lack the means, but because the universe itself has made that path inaccessible. And yet, within that limit lies creativity. Instead of pushing beyond the speed of light, we work within its boundaries. We bend paths, we harness frequencies, we manipulate photons for computation and encryption. We create quantum entanglement. Schemes not to exceed the speed of light, but to explore the peculiarities of connection and information. The frontier remains vast even within the speed limit, full of challenges and discoveries. Every photon used in a quantum network, every pulse of laser in a gravitational wave detector, every beam of light in a laboratory experiment is a step further into understanding, taken at the one speed nature permits. There is serenity in this constancy. While matter erodes, while energy disperses, while time marches unpredictably in human affairs, light remains, always at the same speed, always carrying the same truths. It may seem paradoxical that something so fast could also be so stabilizing, but that is the paradox that defines light, swift yet grounding, fleeting yet permanent, elusive yet revealing. To ask what makes light the fastest thing in the universe is ultimately to ask why the universe must have a limit. That limit, encoded into the heart of nature, is not arbitrary. It is what allows clocks to tick, what permits memory to be meaningful, what lets stars shine and galaxies spin in harmony. Light, with its faithful, unchanging speed, is the compass needle at the center of it all. And so, light becomes not only the fastest entity in the universe, but the most essential thread in the cosmic tapestry. It is both the medium and the messenger, the journey and the metric by which all journeys are measured. While it possesses no mass, no rest frame, no sensation of aging, it nevertheless imparts order to a universe that might otherwise descend into incoherence. Its constancy enables a chain of causality that holds steady from the scale of particles to the sprawl of galactic superclusters. Without it, energy would lack direction, space would have no measurable interval, and time would lose all reference. Light, in its ceaseless travel, reveals to us a universe that is not static but dynamic, not random but governed, not chaotic but ordered by profound and elegant principles. Even as it moves at this unparalleled speed, its effects ripple outward. slowly, subtly marking the boundaries of our knowledge. We learn not all at once, but as light allows, in cadence with its arrival. The grandest events of cosmic history, collisions of neutron stars, the explosive deaths of massive suns, the acceleration of galaxies become known to us only when their light reaches our eyes. In this way, the speed of light does not merely define how fast something travels. It dictates when something becomes real to an observer. Until light arrives, the event might as well not exist. This delay is both limitation and gift. It means that we can never witness the universe as it is, only as it was. But it also means that the cosmos becomes a vast archive of moments preserved in light. At any given time, we are seeing events that span a full timeline. The moon as it was a second ago, the sun as it was minutes ago, the stars of Orion as they shone hundreds of years ago, and galaxies whose ancient light is only now breaking into. Our telescopes from the dawn of time. The night sky, then, is not merely a spatial vista. It is a temporal one, a dome not of presence, but of preserved history. And in that history are clues not only to what the universe is, but to what it will become. Light informs us of structure, where matter clumps, where voids stretch, where gravity binds, and where expansion wins. As light moves, it carries with it the imprint of all that it passed, influenced by fields and particles, bent by curves in space, colored by the temperatures it radiates through. We can reconstruct entire cosmological models from the data encoded in its paths. The entire discipline of observational astronomy relies on this, that the information reaching us has been preserved in light, shaped only by known interactions and not degraded by its relentless journey. Light is also democratic in a unique sense. It is indifferent to scale, to direction, to observer. A single photon does not care whether it began in the fusion furnace of a distant star or in the controlled hum of a laboratory laser. It moves with the same resolve, and to all observers, in all directions, regardless of how fast they move, the speed of that photon remains the same. This property of invariance, central to Einstein's special relativity, defies classical expectation. In our everyday world, velocities add and subtract. If you run inside a moving train, your speed relative to the ground is different from your speed relative to the train. But not so with light. No matter how fast you chase it, it always moves away from you at the same speed. This constancy reconfigures our notions of time and space, requiring them to bend and adjust so that light speed can remain untouched. From this reconfiguration arises one of the most transformative ideas in science, that time and space are not absolute, but relative, depending on motion and gravity. The speed of light is the pivot around which this relativity turns. It is the fixed reference in a shifting world. Without it, there would be no way to anchor one observer's time to another's, no way to reconcile different perspectives into a unified picture of reality. Light speed is the key that unlocks the reconciliation of seemingly contradictory viewpoints into a coherent universe. We see this especially in the realm of high-energy physics. Particle accelerators, like those at CERN, hurl protons at velocities approaching the speed of light. As they near this boundary, their mass effectively increases, and time slows down for them relative to stationary observers. These effects, predicted precisely by relativistic equations, are confirmed again and again by experiment. The fact that we can predict, control, and utilize these phenomena is a direct consequence of the trustworthiness of light speed. It is not a guess. It is a measurable, repeatable, inviolable reality. And beyond physics, beyond astronomy, light has shaped the very way life has evolved on Earth. From the earliest photosynthetic organisms to the human eye, life forms have evolved to interpret, harness, and respond to light. Plants grow by capturing photons from the sun. Animals perceive their environment through patterns of reflected light. Circadian rhythms, hormonal cycles, and even behavioral patterns are tuned to the dance of sunlight and shadow. Entire ecosystems revolve around the light that reaches Earth, which itself is filtered, refracted, and absorbed in rhythms that light's constancy makes reliable. Human culture, too, has been deeply influenced by light. Our myths, religions, and philosophies are filled with symbolism drawn from its power. Light as knowledge, as truth, as divinity, as awakening. Long before we understood it scientifically, we revered it. We chased it in art, measured it with sundials, directed it with mirrors, and captured it with lenses. The technology of optics, microscopes, telescopes, cameras, fiber optics has opened new worlds, all predicated on an intimate understanding of how light moves and behaves. Each advance, each device, is a tribute to our growing relationship with this fastest of entities. Still, light is not just a utility or symbol. It is the boundary between the known and the unknowable. The observable universe is limited not by how far it stretches, but by how far light has had time to travel since the beginning. This sphere, estimated at over 93 billion light-years across, contains all that we can see, all that has sent photons in our direction since the first light broke free from matter. Beyond that, there may be more, perhaps infinitely more, but we cannot yet know. Light has not arrived from those regions, and until it does, they remain outside the domain of knowledge. This, perhaps, is the most poetic outcome of light's speed, that it not only reveals, but conceals, not only illuminates, but defines the edge of darkness. It gives us all the tools to know, but also outlines what is not yet knowable. And in doing so, it inspires continued curiosity. For within every beam of light lies the possibility of discovery, a new planet found by the flicker of a passing shadow, a new galaxy observed in infrared, a new insight born from a particle of light striking a sensor. The speed of light, then, is not merely a number. It is the pace of understanding, the interval of revelation, the drumbeat of exploration. It is what lets us trace the spiral arms of galaxies, map the skeleton of the cosmos, glimpse the flash of particles unseen by the naked eye. It is the fastest thing the universe allows, not because it was chosen to be, but because it must be. It is the rate at which the universe permits change to be noticed, truth to be revealed, reality to be shared, and in the silence between stars. It is light that breaks the void, not as a roar, but as a whisper carried on time. Its motion does not tear through the cosmos with reckless force, but with grace, as if it knows the weight of the secrets it bears. This gentle yet relentless traveler has never paused, never rested, never faltered, for to do so would contradict its very nature. Born without rest mass, light has no choice but to move, and move at the only speed the universe allows for something so unburdened. This motion defines the edge between stillness and possibility, between isolation and connection. And through that connection, we come to know not only the external world, but the deep and invisible laws that govern it. It is not only light's speed that makes it central to our understanding of reality, but its consistency. Whether it emerges from a firefly's glow or a pulsar's beam, whether it is generated in a laboratory or the thermonuclear heart of a star, it adheres to the same rule. This rule, travel at precisely 299,792 kilometers per second in vacuum, is not subject to negotiation. It is not a result of external conditions or varying contexts. It is foundational. This consistency is what allows scientists to rely on light for the most sensitive and precise measurements in human history. From defining the meter to calibrating the most accurate clocks on Earth, from tracing gravitational waves to pinpointing cosmic expansion, light provides the only standard that never wavers. Even in fields far removed from astrophysics or quantum mechanics, light remains a cornerstone. In medicine, imaging technologies like X-rays, MR is with radiofrequency pulses, and optical coherence tomography rely on different parts of the electromagnetic spectrum to see inside the human body. In agriculture, remote sensing with satellite. Light data helps track crop health. In security, optical scanning systems analyze reflections and light diffusion. And in everyday life, light is the channel through which data flows, from the fiber optic cables beneath our oceans to the tiny LED indicators on our devices. These are not metaphorical uses. They are all grounded in light's real and practical behavior, in its swiftness, its flexibility, and its predictability. The universal speed limit enforced by light is also the shield that protects cause from being overrun by effect. It ensures that events unfold in a consistent order for all observers, preventing contradictions in the narrative of spacetime. For example, when one particle emits a signal and another receives it, the time ordering of those events is preserved precisely because of the finite speed at which light propagates. If information could travel faster, then under the rules of relativity, there would exist frames of reference in which the effect could be observed before the cause. This would lead to a breakdown of logical consistency, a universe where past, present, and future blur into an unusable confusion. Light's maximum speed prevents such paradoxes, maintaining the directional flow of time and giving a dependable structure to experience. This is why light's speed does not merely define motion, it defines the arrow of time itself. While entropy explains why time moves forward from less to more disorder, light gives it a shape, a texture, a measurable rhythm. Without a consistent mechanism for transmitting influence, entropy's flow would be unmeasurable, indistinct. Light, by carrying energy and information with unwavering precision, lets time have a character. It ensures that signals cannot leap ahead of their sources, that knowledge cannot arrive before the event it describes. This subtle boundary between what can be known and when it can be known is crucial. It separates science from speculation, experience from imagination. In a way, then, light is the keeper of realism in the universe. It ensures that the map corresponds with the territory, that the signal corresponds with the event. It is the spine of every observation, the carrier of every scientific insight. The laws of thermodynamics, the principles of field theory, the structure of atoms, these are all studied and confirmed through the behavior of light. It illuminates more than just the material world. It illuminates the laws that make that world intelligible. Yet, light does not travel unaffected. Though it is not slowed in vacuum, it is shaped by the contours of spacetime. When it travels through a gravitational field, it bends. This was famously confirmed in 1919 when observations of a solar eclipse revealed that starlight passing near the sun appeared slightly displaced, validating Einstein's prediction of light bending under gravity. This discovery was not just a triumph of theory, it was a direct observation of light's path being dictated not by straight geometry, but by curved space. It revealed that gravity is not a force pulling at light, but a distortion of the terrain through which light moves. Even light, the fastest thing in existence, is not beyond the influence of mass. It follows the shape mass creates. This truth reshapes how we think of light speed. It is not just about how fast, but about how faithfully. Light always travels at its constant pace in a vacuum, but what looks like a curve to us is, in fact, light moving straight along a bent spacetime. This distinction is subtle, yet powerful. It means that to understand the path of light is to understand the curvature of space itself. Observing light's deflection, delay, or redshift tells us not only about the light source, but about the invisible terrain it crossed. It allows us to study black holes, dark matter, and the large-scale structure of the cosmos by watching how light reacts to the unseen. And even when light appears to vanish, it teaches. In the depths of a black hole, past the event horizon, light cannot escape. This is not because the black hole traps light like a net, but because all paths forward lead inward. Space-time itself is warped such that the speed of light, though unchanged locally, can no longer lead outward. It is as though the surface of reality is tipped steeply inward, and the fastest speed possible still leads down. Light's absence becomes as informative as its presence. We map black holes not by their glow, but by the shadows they cast, by the gravitational waves they cause, and by the way they distort the background light. Even in silence, light speaks. Photons, though massless, do carry momentum and energy. They can exert pressure, as evidenced by solar sails designed to catch sunlight like a breeze and propel spacecraft. This pressure, gentle as it is, demonstrates that light is not merely symbolic. It has substance, influence, and capacity for work. This duality, massless yet forceful, invisible yet revealing, limited yet limitless, is what makes light so enigmatic and essential. Ultimately, light's supremacy in speed is not a byproduct of its power, but of its nature. It is what it is because the structure of reality demands it. There is no faster thing, not because light outruns everything, but because nothing can. Take a step beyond the pace at which the universe permits change to travel. Light is the universe's ambassador to itself, always on time, always at the maximum, always translating events into perception, and perception into knowledge. In our minds, too, light shapes experience. Our eyes are attuned to the narrow band of wavelengths we call visible light. But beyond what we can see lies a spectrum as vast as the universe itself. Radio waves longer than cities, gamma rays more energetic than stars. These forms of light exist beyond sight, yet they are all governed by the same rules, move at the same pace, and carry the same reverence for order. They remind us that the universe is broader than our senses can contain, and that light, in all its forms, remains the silent courier of that broader truth. There is something almost reverent in the realization that the universe chose light as its ultimate courier. A presence that is everywhere, yet always in motion. A phenomenon so fundamental that the laws of physics seem to wrap themselves around its behavior. From the faintest glimmer reflecting off a drop of water to the blinding flash of a supernova halfway across the universe. Every appearance of light speaks to the same story, one of perfect speed, faithful transmission, and absolute consistency. And as we examine its role more deeply, it becomes clear that light is not merely a feature of the cosmos, it is the very expression of its rhythm. Even our human journey through science has been paced by our deepening understanding of light. In antiquity, light was misunderstood as either particles emitted from the eye or mysterious rays traveling instantaneously. With time, lenses and prisms revealed that light could be bent, split, and focused. The discovery that white light could be dispersed into colors showed that light carries structure, that it can encode information in its oscillations. When the wave theory of light emerged, it explained phenomena like interference and diffraction, showing that light can add and cancel itself, that it behaves with elegance and complexity. But the wave theory alone could not explain everything. Enter the photon, the quantum of light. With the realization that light is not only a wave, but also a particle, a bridge was built between two seemingly incompatible worlds. Quantum mechanics, strange and uncertain though it seemed, had to make space for light's duality. And in doing so, it revealed even more about the universe. It showed that light can exist in states of superposition, interfere with itself, and even be entangled with other particles. And yet, even as it obeys these puzzling laws, its speed remains unaltered, undisturbed. The wave-particle duality complicates our understanding of what light is, but not how fast it moves. As we harness light in quantum technologies, we also confront its limits. We cannot clone a photon. We cannot measure it without altering it. We cannot extract more information from it than the universe allows. These limitations are not flaws. They are principles, guardrails that protect the coherence of the quantum world. And throughout all of these principles, the speed of light is a thread that never breaks. It unites the unpredictable behavior of quantum particles with the structured motion of celestial bodies. It links the smallest and the largest realms, allowing a continuity of laws and measurements across the entire scale of reality. This continuity is reflected in the cosmic background light, the afterglow of the universe's earliest moments. That light, though now cooled and stretched into microwaves, still carries the fingerprints of the birth of structure. Tiny fluctuations in temperature and density that seeded the formation of galaxies and clusters. When we map this background, radiation, we are not just seeing a surface. We are reading the diary of the infant universe, its earliest entries preserved in the only language the cosmos speaks fluently, light. And yet, the very expansion of the universe means that some light will never reach us. Distant galaxies are moving away so rapidly that their light is being stretched beyond detectability, or even beyond the bounds of space we can ever see. These regions are receding faster than light can bridge the gap. Not because they are breaking the speed of light, but because the fabric of space itself is stretching. This phenomenon, a consequence of cosmic inflation and dark energy, means there are events whose light is forever unreachable. The visible universe is not all that exists. It is only what can be revealed to us at the speed that light travels. Even so, the light that does reach us continues to carry treasures. In the interstellar medium, it uncovers the chemistry of gas clouds. In the atmospheres of exoplanets, it reveals the signatures of water, methane, and carbon dioxide. In the swirling disks around young stars, it shows the building blocks of planetary systems. And in the oldest stars of our own galaxy, it preserves the memory of elements forged in long-dead predecessors. Every photon arriving at our detectors is a time capsule, a memory, a fragment of a moment, a clue about the conditions of its source. Our scientific instruments have evolved to stretch their sensitivity, to reach deeper into the darkness and resolve ever fainter light. Space telescopes like Hubble and James Webb extend our sight beyond the optical range, revealing forms and structures that our eyes were never meant to see. With them, we look back across time, not because we have built machines that defy the laws of physics, but because we have learned to work with them, to respect light's limits and exploit its constancy. Light, then, becomes a kind of promise. It tells us that if we wait long enough and look carefully enough, we can uncover truths that were once hidden. It assures us that even in silence, even across incomprehensible distances, knowledge can travel. It reminds us that we are not separate from the universe, but are shaped by the same rules. Every breath we take, every step we make on Earth is governed by light's presence, warming our planet, setting our biological clocks, filling our world with color and contrast. Yet for all the complexity and wonder it brings, light remains humble. It does not impose its speed, it obeys it. It does not dominate the cosmos, it illuminates it. And even as it rushes forward at the fastest possible pace, it does so with quiet elegance, making the invisible visible, the distant near, the past present. What makes light the fastest thing in the universe is not that it tries to be, but that the universe has given it that role. It is the purest expression of motion unburdened by mass, the simplest and most faithful traveler from one point to another. It does not need permission, and it cannot be surpassed. All our hopes to understand, to communicate, to see, hinge upon its movement. Thank you for watching this video from the Sleepless Scientist. We hope this quiet journey into the heart of light brought you a sense of peace, wonder, and perhaps just enough curiosity to guide you into dreams filled with stars. We are deeply grateful for your time. If this video made you think, or if it accidentally kept you awake, we sincerely apologize. Please don't forget to like, share, and comment below with your location and the time where you are. Whether you're drifting into sleep in the quiet corners of the world or just waking up under a rising sun. Now, let go of the thoughts. Let light do what it always does. Move gently across the silence. Allow yourself to fade into the softness of rest, accompanied by calming sounds that follow this video. Inspired by the universe's quietest whispers.